Hello, James.
Hello, Jawad. How are you?
Doing well. How are you?
Enjoying my morning
Uh,
extra coffee?
Yeah, mm, I need some of that myself. Just looking at the stock market. So
Maybe throw a little something extra in with the coffee after seeing the stock market this morning.
that's right. Yeah.
Good Lord.
Hello, JP. Is that you?
Hey Jawad, hello everyone. This is JP. Yeah, my name is actually showing my son's name. Let me change my name. Yeah.
Okay. As always, we wait for a couple minutes. And
Morning, everyone.
hello, hello.
Hey David.
Okay. I think we are pretty close to 10:03. So welcome everyone to the proof of concept workstream. I'm assisting JP, who has led the charge on this work stream for a long time. And um, we wanted to just do some deeper thinking about, maybe looking at the charter of the work stream and looking at some of the historical activity that the work stream has done, and then maybe think a little bit about the future work and future plans, especially after some of the requirements that were put out by NAPMP from US CHIPS Act, which may still be alive, I don't know. But some of the requirements that they put out there were pretty aggressive and interesting. So one of the things that we have been thinking at OCP is to basically bring some of those concepts into the proof proof of concept work or prototype work that we have historically done in this work stream. So JP, I'll hand it over to you at this time and be happy to chime in a little bit later.
Sure, Jawad. Thank you. Yeah. Good morning, everyone. My name is Jai Prakash Go by JP. I work for D Matrix in Santa Clara. And I led this POC work stream for several years. Perhaps we started this POC work stream somewhere around 2019, if I remember correctly. And we continued very aggressively at different projects until 2023 or 2024, if I don't remember correctly. And later we had some issues, and especially with the funding and the projects. And we try to restart and see if there is further any interest in actually going further. and what can we do in the POC work stream as a part of ODSA project, right? So I think Quinn is also joined. Hi, Quinn. So Quinn was very much part of this, the POC work stream early on, helped to define the Mara baseboard platform. So what I do is first actually, I'll kind of go over the history, what has been accomplished in this work stream so far. And then I'll hand it over to Jawad. Jawad will give some more idea about what we can do in the as in going forward, and then we'll do more brainstorming on that, right? So that's a high level idea what we want to accomplish today. So let me share my screen and give you an idea of what has been accomplished so far in the POC work stream. Let me share my screen. Okay. Yeah, so do you see my screen?
Yes.
Sorry, presentation mode slideshow. Yeah, so the main charter, when we started this POC back in 2019 or so, the main charter was there wasn't any chiplets at the time. So and people wanted to experiment with different ideas. So we wanted to create a reference design. So the Workstream charter was really to create reference designs and flows that can be broadly used across the industry. You leverage the industry knowledge and develop these reference flows that can be collectively used in the industry. So that was the POC workstream charter, and still actually holds this activity. If we identify a common problem that'll be useful across the industry that can be shared, it's still a great value proposition. That's what we want to explore as a part of the POC workstream. So let's actually look at the history, what has been done so far. So actually what this workstream delivered the Mara baseboard and the pitchlets. We demonstrated that in the 2021 OCP Global Summit. And I'll go over the details. What is the high level details of the Mara baseboard? And the second accomplishment is actually we developed the package for BOW test chips. So there are two companies develop BOW test chips based on the specs developed at ODSA, D-Matrix and Blue Cheetah. And we developed a test package to prove the interoperability, right? The test package has been, the layout has been completed, and it's archived in the Google Drive, ODSA Google Drive folders for anyone who wants to take a look at that. Right, so I'll go over the details of that, what this test package is all about. And the third is actually, we were actually specifying that open platform for test chips bring up. So in the we were actually on embarked on test chip, test pack interoperability testing with the test chip package. And we needed a platform for testing this interoperability, PCB platform. And we realized everybody in the industry has the same need, and we want to develop an open platform. So a lot of work has been done on this open platform specific definition, and I'll share that as well. Right, so that's the high level. What I'll go through it today, like the 3 projects that has been accomplished. So I'll take a pause here. Any questions, any thoughts before I go into the details of the projects? Okay, so let's go into details. If there are no questions. So this is the project I think we demonstrated in OCP 2020. So this platform, what we call as a Mara baseboard, this was developed in collaboration with Facebook. And so this platform, what it is, it's a PCI card, and it has got 3 slots for attaching the what we call as the pitchlets. Since at the time there was no chiplet concept, chiplets were not defined at all. We want to emulate that concept with the PCB So software ideas can be prototyped, right? Any chiplet accelerators can be prototyped. And we define 3 sockets. In these sockets, we can bring in either, we can emulate the chiplet using a PCB, or we can attach actual chiplet itself on a daughter card, right? So this has got a very rich connectivity between the chiplets and the host. And the host connectivity is actually through a PCIe Gen 4 link, and it'll actually exercises the able to run the test on this chiplet pitchlets. The concept of pitchlet came because there is we used a notion of chiplets on the silicon, and if you translate that in the PCB, we call that as a pitchlet. And this platform is very self-contained, has got power, Ethernet, and then it's cooling as well. And so each of these pitchlets can support power about 100 watts, 50 to 100 watts of power. And the idea is to mainly prototype ideas. The main thing for this is anybody who wants to try out chiplets. There wasn't any platform available, right? If you want to try software ideas, this platform would allow to prototype. So we demonstrated storage accelerator applications with the concept of a chiplet using this pitchlet idea in this platform. Right, so 3 companies contributed to it. One is actually the LX2 multi-core ARM CPU from NXP. So NXP contributed this pitchlet, this particular socket, the socket on the rightmost. So this is actually an ARM core CPU that can be put in on let's say on a die, but this is actually packaged onto a PCB, and that can be used for all control and accelerator applications. And this directly talks to an NVMe drive on the top. You can see there are 2 NVMe drives. So you prototype this idea, prove the concept before taking into an actual chiplet. And then there is an FPGA on the board from Lattice Security and Control Applications. This pitchlet, this module is contributed by Lattice, and is mainly for any type of control or security applications involving chiplet-based accelerators. And the first one is actually a Broadcom NIC, and this is contributed by Broadcom. And this has got a 200 gig NIC that you can attach flexibly in your prototyping platforms. That can and this was the whole. These 3 pitchlets actually were used to demonstrate a storage accelerator application in during 2020 or 2021 OCP summit. Right, so the details of this is available in Google Drive. If anybody wants to look at the details, I'll be happy to share, point you to the link we have. And also we have the boards available if anyone wants to experiment or prototype any other ideas on this. And the platform also comes with a rich software for controlling these pitchlets. And the basic idea is essentially quickly prototype any ideas that you may have using these building blocks. And the spec is very flexible. You can also come up with your own definition of a pitchlet. So if you want to have your own pitchlet idea, so the specs are available. You can design and plug it into the socket. Right. So this was, yeah.
JP, now that I'm thinking about this one, so one thing I recall, this work coincided with the development of OAI and OAM modules at OCP, right? I recall there were some discussions on similarities of the two, but they were largely independently developed, right? And the other thing I remember at that time, there were really no standards for BOW or anything of that nature. So we were really limited, and we defined this whole thing using PCIe. And one big idea that we had was that for every chiplet provider, they can provide a development board in this format, and the integrators can then piece them together and kind of like form a bigger system that they can do software development on or do performance modeling on, right? That was the big idea. But at the same time, if they can integrate those chiplets into one module, they can theoretically place that one module in one of these slots, right? And then basically scale up the system more and more, right? So what would be interesting in my mind, if we someday, if there is interest, we dive a little bit into what architecture that was and see maybe now with advancement in UCIe and BOW, is there an alternative version of it that we can potentially create that may be useful for interop or software development?
Mhm.
I don't get this at all. You know, the world has moved on, right? This is not viable for any kind of chiplet conversation, in my view. So why are we, I mean,
So, hi, Akash. I think
I
what
mean,
you're referring to is the bandwidth, right? Chiplet bandwidth are much higher
well,
than what.
no, I mean, chiplets are for short reach, right? You need to put multiple chiplets together, and that's where you failed last time. So why don't we address the issues and talk about that, right? This is not a viable, you know, build a PC board, which is an emulation of a chiplet, so you can emulate something else. I mean, just use a big honking FPGA. Doesn't prove anything, right?
Yeah, yes and no. I agree with your perspective, but it's if you mainly this platform was created to develop software early on, right? That
No, I
can
get it, but
prototype ideas.
that's what people use FPGAs and emulators for already. I mean, it's a solved problem.
Um, True, but yeah, this is actually an FPGA will solve it. But let's say you want to try prototype the different components, right? Like for instance, here you have an XP CPU, you have Broadcom NIC, and those I/O connectivities are not very rich. You have a big FPGA that you can prototype, but you will not have different components that you can flexibly bring on, right? So it depends on what you want to accomplish. If the goal is actually a software prototype idea and test it, this is a good platform. If you prototype the chiplet itself, this is not a suitable platform for that.
So a bit of a history.
Yeah.
We did start with exactly that reaction that you have, and because on day one we wanted to build a chiplet POC, and Quinn and JP can tell you a number of issues that we ran into, and this was a take a step back. We're not saying that today we have to do this. It's just history, and there are lessons that that's pretty much it. You know,
Right.
what would be a solution to today to do interoperability? And I'll tell you, based on what I see, chiplets are not easily accessible anyways. So nothing really has progressed much at the POC level because of closed ecosystems. So the big question in our mind is, how do we open up the chiplet economy with some of these ideas and discussions? But your
Yeah, no, I completely agree with that letter statement. That's what we should be focused on. Okay, open chiplets don't exist. There are a bunch of issues. Let's talk about those, right? The fact that 5 years ago, I mean, frankly, you can't buy an NXP chiplet today, right? I mean, this is 5 years after this device. I mean, it's got no relevance to chiplets in that sense, right? So
Oh.
I think,
But Can I jump in with one thing? I think there are many, many things at that time and still that you could view as important. And one of the things that we intended this to be, this is not intended to really test spies or any of that. One of the main things this was intended to do was to think about how you'd program, how you'd bring up and program and develop, assuming you had chiplets. And so part of this was more of, let's say, it's not the hardware. This is really more of a system and software POC that we had to build some hardware for, was the intention.
Okay.
All right, so then going back to the chiplets and the closed ecosystems, one of the big unknowns for us is really how do we make this work end to end? And so even if you didn't have a concrete artifact, an actual package that contains a bunch of chiplets, understanding what are the necessary steps, who can and will do it, and what the approximate costs are can be important. The spreadsheet model that's been created under a different working group has been informative, except it's also confusing because it doesn't say who does what. And secondly, it has a lot of free parameters on it that an outsider can't figure out what a reasonable number would be to fill in, like open-ended yield rates and things like that. So, for this POC effort, if you could at least even line up, without even building anything, line up what the end-to-end entities for proof of existence that this can be done and with the existing players in our economy, that would be a really big contribution.
Hey, can I just ask a really stupid question here, guys? So what exactly is a P chiplet? In my mind, it's a breadboard of a function that eventually will be chipletized. Am I completely out in left field, or is that close?
Yeah, John, that's correct. That's a good description of what you're describing.
Okay. And so to me, in that case, PCI Express makes a lot of sense, because one of the nice things about UCIe is how it's leveraged on that ecosystem as far as connecting system components together. It's kind of a genius move by Intel and a natural evolution as we move from baseboards to interposers and so forth. It almost seems like there's two things going on here. One, and I completely agree with the concept of accelerating the software development on one of these systems, because you cannot wait until the silicon is back from the fab to building software. And so if you can just get the software functionality all tied together and working with emulated or breadboard pieces of the hardware that are eventually going to go into the system, you're way ahead of getting to market. And all of these chipletized systems are going to have software in, right? I mean, that's just almost by definition. And then to me, the prototyping of the chipletized processor itself is almost kind of a separate issue, because now you're talking about electrical things running around and cross-talking and all that have to be fixed before the software can know that it has a reliable system that it's working on, and it's not going into the weeds because you had a bad memory fetch instead of a logical error in the code. So this all ties together kind of a really complicated system design problem. And for us to be successful, I think we've got to solve both of those.
Well, that's fine. It's like in the business group. I mean, we've started to think about the concept, and I think they're going to start, of how do you simulate, I mean, at the very basic level, can you get a model of a chiplet? I mean, we're forget building a breadboard of a chiplet and a PC board, which takes a lot of effort, right? Because you know there's a zillion processor versions out there, right? So and somebody wants to evaluate how the whole system is going to come together. So there needs, so that was one area that we've been discussing, and then going and talking to EDA people and stuff like that. Is System C the answer? I mean, I don't know. That's some input that people need to provide.
Well,
But the concept being, could you standardize? Could we work with people who are doing models, right, and build a UCIe model, a bow model, and whatever security, and how would somebody put this together? So not only could they eventually see how to bring it up and does it communicate, but even do some performance modeling depending on how advanced you get, right? I mean, that seems somewhat logical, because you can then have, but here what I see is you're so limited by the chips you can get and the distances, and so getting something useful may not be, I mean, we could spend a lot of time and effort doing boards and then 3 years later find, well, it wasn't much use, right? That's my concern. Whereas
Right.
if we could get people doing different chiplets, let's take, somebody says, I've got, an IO chiplet, right? Let's take Alpha Wave. I mean, at some point they have a model of that, right? They have certainly at Verilog, right? I mean, they don't want, they probably are not going to want to disclose that. But now, can they work, or can we convince people who are doing that to say, hey, if you want to sell your chiplets, let's go with, a high level model at least, that people can see if it'll work. And I know, is it Mukesh? I forget, the gentleman from MIPS is starting that other project, right? The system level of how do we tie these chiplets together? Because two chiplets, even if they have the same PHY from the same vendor, if we don't know what's behind that PHY, they're not going to talk to each other, right? I mean, at a system level, right? So
Right.
I think that's the bigger problem of how do you build, how do you validate, how do you even start, right? And I see where you were going with this, which is, okay, we don't have anything. Let's take what exists that might be, so you've got Ethernet, you got PCIe, but but the eventual chiplet may want to use, all sorts of different packaging, and as it's very difficult, right? So, and then from John's point, you don't know how much any of this damn thing costs. So I think at least as chiplets come along, you can say, well, this group that's defined by this System C model, or whatever the model is. I don't want to use System C because I'm now mandating something. I don't want to mandate. Whatever the modeling approach or the best solution is technically from the system guys to say, hey, we can use this. They can then start saying, okay, this is going to cost you $2 or $5 or $10. I mean, trying to get a customer or somebody evaluating to try and look at a die size. And now, if you're going to do your own chiplet, then yes, you have to get down to that point, but you should be able to get all the other chiplets you're going to use, whether it's ARM based or RISC-V based or Ventana based. I mean, there's a number of people developing chiplets, and if we could get those people to deliver something that somebody could put together, and it's in everybody's interest, right? If you're developing a chiplet and you can't talk to anybody else, you're shooting yourself in the foot, right? So I think that was kind of my point of view, was, okay, I know there was this effort. I'm glad to see, I've seen this slide before, and I was like, okay, that was a year or two ago. So anyway, so if we're going to go down the pathway of trying to build PC boards, I think that's not necessarily a good way to do it.
Yeah. So if we does anybody have access then to a decent FPGA based model for bundle of wires or UCIe? Because there are a number of efforts that would like to model the chiplets using an FPGA emulator or simulators where we insert timing delays in order to make it actually cycle accurate.
Yeah. So
and for lack of having a UCIe model, that's what's held back all of those efforts. So if we could come up with a UCIe or a bow bundle of wires model, then there's a lot of different efforts that would be happy to deliver.
No, that's a great input. I mean, I'm aware of some people that are developing one. We don't have one for ours, but we've talked to a company called Circuit Sutra who develops System C models for companies like ARM and others, right? So we definitely buy into you know, at least having a high level model. I mean, people may not be willing to give, anything with proprietary technology, but as a first blush, you want to just say standard UCIe, right? Give me a model for
Yeah.
advanced packaging and standard package. I mean, Christ, I mean, let's get something going, right? So,
Any model. do.
So, so
Yeah.
John, when you're talking a model, are you talking like a link layer model that gets implemented into the FPGA fabric? Is that the level you're thinking on?
Yeah, I mean, so it has to be modeled. The UCIe has its own kind of protocol, but it also
Right.
needs to have inserted into it the delay, like a delay line that simulates the actual SerDes, the physical interface, and the delays associated with the physical chip-to-chip crossing. So, so right now, for example, in most of our designs, we assume that probably we would run AXI over the chip-to-chip interface. So that would be the protocol that we're speaking in our project, but we would like to break that AXI interface into two pieces and insert into there something that simulates the behavior that the actual UCIe interface would have for the chip to chip. And it's going to have additional delays. It might have, retimers. I don't know, but we don't know what should we be dropping in there other than a delay. And I think a delay is too naive. I think that these UCIe links are more complicated than that.
Yeah, and I would agree with that for sure.
Okay, yeah, yeah. Thanks, Kash and John for the inputs. Yeah, I am. Yeah, I mean, the suggestion is not to actually continue this effort, just reviewing the historical what has been accomplished. And I hear you, Kash, about the models, what you're asking for.
Yeah, JP, but I think we should keep out an open mind. So there's a lot of history and a lot of reasoning why we did some of this. And I'm not saying it's gonna be exactly useful today, but there are gems in here that we probably should think through a little bit. So I wouldn't just completely throw it out of the door, right? So
Absolutely, yeah.
Yeah, Jawad, I agree with you. I think this is going to be, there's definitely, I think, great use in this, in being able to bring up a chiplet, right, without having to build the most expensive substrate and you tape it out and you sink all that cost only to find out that you have some other problem, right? Well, so basically, in parallel, right, if you're getting chiplets from elsewhere, and you can quickly start bring up of your own silicon to validate that it works and do the software development while the package testing work is ongoing. I think that's going to be extremely beneficial. I think the comments about the modeling and performance modeling are very relevant. But right, that's a little bit further earlier in the flow. The one thing that actually, I don't know if you guys know, but in CDX, so JP, when you started with your presentation, looking at reference flow and reference chiplets, actually, we are kind of doing that in CDX right now, right? We came up with that white paper that talked about workflows for integrating chiplets. And we are kind of trying to get a demo design, actually, that kind of exercises that workflow, starting from how you do definition, how you do SI planning, PI planning, power thermal, right? And the performance piece is actually very, very relevant. I know that the modularity workstream, they have kind of a model. I was just talking to Patricia this morning, a model of what a AI workload looks like, but they're also struggling trying to figure out, okay, how do we figure out what is going to be actual performance in that based on different widths and stuff like that. So we are also struggling with having lack of HBM models and UCA models. So I think that's very relevant. So I think this effort is great, and it's very complementary to what everybody else is trying to do. In the sense that, right, we in CDX are trying to build actual chiplets, at least demo chiplets, right, with some funny technology. Modularity is looking at performance, right? How the hell do we do performance analysis? So I think this kind of fits very, very nicely with what everybody else is trying to do, right? There's so many different faces to this chiplet problem. I think it's very useful if we attack it from all sides. But I mean, right, there's so many pieces that we need the contribution from everybody.
Yeah, thanks, David. That's good to know that you are developing the flows for the chiplets. Yeah, maybe I'll attend one of your meetings to gather more data.
Yeah, that sounds really good. And is this actually, are you naming names for people that would fulfill that part of the flow, or?
We have contributions from all different places. Siemens is contributing, we are contributing, we have Georgia Tech is contributing as some of the manpower, and also contributing some of the rules for the glass substrates that they have. So we're kind of playing with that a little bit. Some of the things we are kind of I'll use the word substituting instead of faking, right? Right. Basically, we are substituting actual UCAE for our made-up UCAE, right? Because we don't have it. But if you're looking at the flow and floor plan and things like that, it's the same box, right? Whether you call it UCAE or my UCAE, it doesn't matter, right? It's just different technicalities about how you would run a tool, not necessarily what you need to do, right? It's still the same mental approach to doing it. And hopefully, we were just talking this morning, first iteration, we're going to do 2.5D. Next iteration, we're going to put the memory chiplets on top of the CPU chiplets and the AI chiplets and see how that looks. So that performance modeling is going to be also very, very interesting.
Cool.
Yeah, very interesting, David.
Yeah, but definitely we do have that gap, right? Even with the if these were real chiplets, right? The gap is how the hell do I bring up my system? Right? How the hell do I bring up my system? Right? It's easy if you're getting. I think Intel opened up their or were kind of advertising that they open up a slot on their system, but basically what you get from Intel is everything is ready to go. You just have one slot to plug in your chiplet, right? And that's easy to do. But in a real open economy, you're going to have 10 different vendors for chiplets, and they are supposedly non-good guys. So what do? Do you have to go and build, actually, and design a silicon interposer, pay a ton of money just to figure out how do I bring that up, right? Assuming you have gotten past the point where you have figured out that your performance looks good, you have taped out silicon. How do you bring it up, right? You cannot possibly build the entire substrate, build up everything, and then hope that you can figure out in debug. Can I debug this and make it work?
Yeah.
Well, I just want to go back to John's. You're saying AXI on both sides and UCI in the middle, right? And if you could model that in an FPGA, right, then you actually have a platform that could be used, right, which is independent of the FPGA vendor, right? So, I mean, AMD also had the same thing, right? They've done this thing where they're going to have a chiplet. They call it an anchor chiplet, and then you can hook into the ecosystem. But in reality, it's going to be very difficult to get AMD to even give you a chiplet, okay, where you can do the packaging yourself. It's not happening.
Yeah.
So really, it's only for a few customers who they are willing to work with, right? And I'm sure Intel is in the same, Intel Altera in the same boat. But for general purpose use, I think and Quinn, you're more of a systems guy. I think that does seem like a foundation. If we could find someone who has a model, let's just hypothetically say that there was a model for a die-to-die interconnect that can handle AXI, and then if it was somehow open sourced or something, then customers could actually validate something on a large FPGA. Does that make sense? Or is it viable?
It's certainly what I want to see.
Because you've also got all the, as you know, FPGAs are chiplets already, right? So you've already got an Ethernet chiplet, an HBM ecosystem. So at least you can start really validating your accelerator, yes, at lower speed, but you have a better chance if it's now split somehow into 3 or 4 chiplets. So I don't know. I like that idea. I mean, I think that's something worth having a more in-depth discussion on. Obviously not right now, but I was just thinking of that as after you said that. I think it makes a lot of sense because I can see a lot of people that have experience with the tools already. They've got a chiplet. Imagine the large FPGA is already your emulation system, right? It's got Ethernet, it's got memory, it's got PCIe, it's got all the regular I/O that anybody could possibly want, typically, right? The big devices, and it's got a lot of LUTs. So okay, let's at least go through that process. How? I mean, if we can't make that work within a known good packaged unit, we got other problems, right? So anyway, that's just what I was thinking. So yeah.
Yeah, I think essentially Kash and others, what they're talking about is FPGA prototyping for getting the chiplets up and for validating the chiplet interfaces.
Yeah. Yeah,
Correct.
basically. Yeah, and the protocols that bring up, and also ensuring that the chiplet will be performant in situ.
Right.
They can tolerate the link delays and stuff.
Right.
Yeah.
Okay, in the interest of time, let me continue with that where I stopped
Actually,
here.
JP, can I add one more thought?
Sure. Yeah, sure.
I think the FPGA idea is great. I'm thinking of I think what you want to get to here is a point where instead of the customer giving you models or FPGA that their device performs like that, instead they're giving you a chiplet. Probably chiplet. No, let me find a better word. Chiplety thing, I would call it that, like that you can then plug in your chiplet into and make sure that next level works, right? If you have figured out that the FPGA works, now you got your silicon back, how do you test that against actual chiplets, right? Again, not without building the full substrate, but at least test the functionality, actually all the softwares and everything works, right? Because model is one thing, getting the actual silicon with, how it works is a next level verification. So that's a kind of the thought I had.
Yeah, sure, David. I think, yes, sure, certainly. We should explore that further. Okay, so let me continue. So this is the first project we worked on as a POC work group. And then let me go. The next project we worked on is actually interoperability, BOW interoperability package. And what you see is a 2 dice, blue cheetah analog, and then D matrix. And we were actually developed the whole package. And you can see here, this is the package we developed. The Tessol helped us, and the Google and Tessol were helping us doing this layout for this project. And you can see there are 5 test structures, and with different dies, D matrix to D matrix, D matrix to blue cheetah, and different combinations and different lengths. And this package is ready to tape out. I mean, we could not get we want to have funding to actually prove the interoperability, but unfortunately, we could not secure the funding at the time. But this package itself is a useful reference for anybody who want to study about this chiplet interfaces, signal integrity. The models were developed, and we published 2 papers based on this. One IEEE journal paper was published based on this work. right? So it was a good work. The design is ready to tape out and runs at 16 gigabits, BW 1.0 specs. Right, so this is on the Beaver interoperability substrate. The next project actually we were defining was actually the platform for bringing up the test chips. If you had to look at anybody in the market for the IP market, everybody has got their own boards and then own way of bringing up own software to drive all this, right? So we want to standardize this and offer this kind of universal bring up platform by actually by defining this what's shown here. So in this concept, we'll have a test harness PCB on the left where it exercises all the tests, and then we'll have a DUT PCB. And the DUT itself holds your test chip and gets connected to a control board on the left. So this is similar to an mini ATE, if you think about this. But the key advantage is that you can share a lot of hardware and software across the industry. So there's a lot of software can be developed open source to drive this test chip and test these chips. Right, so we defined all this and it's available. The definition is available in the Google Drive. Again, this project did not take off because of this the funding. I mean, these projects are involved in some sort of implementations and requires some funding. So so at least the definitions are available, and there is further interest from at least a couple of participating companies interested in having this. We can take it up further. Yeah, so this is what I want to share as a kind of history, 3 different projects. And I'll hand it over to Jawad for what we want to do next.
Well, I think we had pretty interesting discussion so far, a lot more in depth than I was imagining. So JP, before I go into throwing some new ideas here, let's talk a little bit about logistics.
Sure.
So I know this work stream has a lot of old IT systems that, so a lot of things have improved at OCP, right? We now have Google Drives and we have calendars and totally different email lists. So do you have a OCP email list for this work stream?
No, we don't have a distribution list.
Okay, so first thing we need to do is we need to upgrade to get a distribution work mailing list, and you do have a Google Drive, right?
Yeah, we do have a Google Drive, yeah.
And you also have the GitHub, right?
No, we don't have a GitHub for this.
Okay, so between me and David, we can probably help you with that. And because I know when we are doing some of this work, it's probably archived in Google Drive, and even though it may not be useful or may not appear useful right now, I think we should archive it at GitHub, all the historical work. David, do you think that's a good idea?
Yes. Definitely, we should find a way to preserve the work in the data. I think it was very useful exercise.
Okay. So one of the action items for me is to talk to Kevin Kiefer and get a email distribution list, and then everybody should just sign up for that. And then that way we don't have to use the main OCP distribution list. We can create a POC one for it. But I'd imagine, JP, you have a list of people that you were using previously to maintain your distribution, right?
Like we have sent out emails. I can dig it up and get the list of people who interact with, who are the participants for this work stream.
Okay. So that sounds good. So I think we will probably need a lot of discussion on this topic before we can get to a charter or like a revised charter and, you know, what next activity we want to work on. So we've already spent quite a bit of time discussing just what was done historically and barely touched on it, right? So I'm not sure if you guys know about this notice of funding opportunity that NAPMP had put out. That was maybe 6 months ago, and a whole bunch of folks from OCP, they did respond. And at this stage, we don't know what's going to happen or how will that whole thing unfold. But the interesting thing was there was a POC challenge in that particular notice of funding opportunity. And in my opinion, we probably should just look at that and use that as the North Star. There's one very interesting concept in there, which is for chiplet sockets. And the challenge was that, you know, think 4 or 5 years down the line, and there is a new interconnect technology called abundance of wires, and build a proof of concept system for that technology 5 years out. So one big commentary on that notice of funding opportunity was that, hey, these guys are just going too far into the future. They should have done something more relevant to where we are and where we may have some immediate commercial opportunities for the participants. So I wanted to, I mean, I'm not suggesting we do that. I'm just mentioning some of these ideas. Let me know, can you see my screen?
Yeah, we can see your screen,
Yes,
Jawad.
yes, Jawad,
Okay.
that's it.
Okay, so what you are looking at here is the latest and the greatest NVL 72 box single tray, one U tall that has a number of Grace Blackwell GPUs, and next you will get the Rubin version of it. It largely would stay the same. And if you deconstruct the system, if this system's mechanical spec was actually contributed to OCP by NVIDIA, it does have a pretty much all the important advanced packaging technology, and they don't call them chiplets, but it's a multi-die design still. And the trend that we have seen from NVIDIA, for example, they don't break the die until they get to the reticle limit. And beyond the reticle limit, they basically start piecing them together. That's kind of the method that they have used in scaling up. So when we were thinking about the government's challenge that they put out, we started to think, how can we respond to it? And their requirement was put 1,000 chiplets on a full wafer scale interposer. Okay, so at this point, you know, this is just a cartoon that you are looking at, right? Which is come up with multiple levels of interconnects. So you may, if you look at those individual squares, that 5 of those that you are seeing on each green panel, each one of those in this concept is actually cut out of a 300 millimeter wafer. And it kind of like is in a way similar to what Cerebras Systems had done, but the way we were thinking about it was that, you know, if there is this concept of chiplet sockets and how they communicate with each other, and sockets are defined for memory and for various other functions, and if there is some kind of a system architecture that gets defined by which was one of the motivations for us to encourage the chiplet systems work stream to think more deeply about the chiplet architecture. But here, um, would we would definitely be thinking about, you know, how physically we can make some proof of concepts going in this direction of creating something that is useful for the industry, and it doesn't have to be 5 years out, but maybe there is something that we can potentially do with all the new BOW work that we are thinking about. So I just wanted to flash this slide here just to provide a thought process uh, behind some of the things that I was talking about. We don't have to necessarily build this thing. I mean, this thing, the way it's shown, is a very expensive and a long-term project. But now that we've seen some of the history of where we started and some of the vision that we have in terms of, you know, where do we want to go, be it with government or without government, we think commercial interest will be the best driver for all of it. So I'm happy to answer any questions you may have because we only have 3 more minutes left.
So Jawad, you mentioned about the government proposal for the Chiplets Act. I missed that part. What exactly is that, and how is it related to this?
So they didn't draw these diagrams, but they did write a long document on the vision. And this is basically translation of that vision by an engineer of what it would look like. Okay. So, you know, the guy who wrote that whole vision is Bapi. Okay. And you know, Bapi was the main instrumental guy behind this work stream. This particular one, right? The proof of concept.
Yeah, absolutely. Yeah.
Right? So this is a important thing in the sense that, you know, we can do all the design and testing and workflows, everything independently, unless until things come together and we make an attempt to actually build a proof of concept, we wouldn't completely discover all the challenges and all the issues. So I think one of the big motivations that NAPMP has is what really was learned by putting that Mara board together. I think that's my reading of it. Okay, so I think we should definitely go in the direction of making test packages and not the test boards. But the challenge that NAPMP has is you have to run software on it. You have to boot this thing up and show some performance. Right. So this doesn't mean that we will be working on this idea in this work stream. I just wanted to just put it out there.
Okay.
So JP, that's the only thing I had to share.
Okay. Thank you, Jawad. I think we are on top of the hour, so I think we request more discussion to crystallize how we want to shape ourselves in POC. There's something we can carve out that is useful across the industry. Is
Yeah.
something we are after. I think it requires more discussion.
Yep.
Okay,
Okay.
thank you all for participating today. We'll catch up more. Yeah, bye now.
Bye.
Yeah, this was a great discussion for first meeting. Thanks, everyone.
Thank you, David.